right? So in my last class, I have discussed one very important topic, that is Gauss law, right? Gauss law states that I have explained in my last class very clearly the statement of Gauss law, right? So we can see the figure, um, inner sphere and outer sphere separated by dielectric material. If an imaginary spherical surface is assumed between inner sphere and outer sphere, the flux passing through, the total flux passing through the imaginary spherical surface is equal to charge on that surface, right? Charge on that surface. That means J is equal to Q, right? J is equal to Q. And I have proved, so there is a proof for the statement, taking a spherical surface, right? And here at the center is Q, right? So taking a differential element here, and flux passing through this differential element is differential flux. Therefore, dψ is equal to d ds, and integrating xi is equal to surface integral ds, and charge density is uniform on the surface of the sphere. So therefore, d can be taken outside the integration, and we have d surface integral ds. And surface integral ds is area. So area of the sphere is 4 pi r square. So 4 pi r square and 4 pi r square will get cancelled. We have psi is equal to q, right? And coming to the point form or differential form of Gauss law, it is also called as Maxwell's first equation. Xi is equal to surface integral ds, that we know. And let us consider a volume charge, right? Considering a volume charge, then we have charge Q is equal to volume integral rho v dv. And from Gauss law, Xi is equal to Q, and we have surface integral d dot ds is equal to volume integral rho v dv. And equation 3, on left hand side surface integral, on right hand side volume integral, right? So therefore, left hand side surface integral can be converted into volume integral by using divergence theorem. And by using divergence theorem, we can convert surface integral to volume integral. Right? So therefore, volume integral of delta dot d bar dv is equal to volume integral rho v dv. Right? So both sides we have volume integral. So therefore, finally we will be having in this equation delta dot d bar is equal to rho v. Right? So that equation we have. Right? So this is nothing but point form or differential form of Maxwell's first equation. And equation 3 is the integral form of Maxwell's equation, and this equation is the differential form of Maxwell's first equation. Right? So that is what we have discussed in my last. Right? So now let us do some problems related to this, and then we will go for Gauss law. Right? And also let us do some problems. Right? So problem 1. After doing problem, I will discuss before I can do a problem. Delta d bar is equal to rho. Right? So this is Gauss law. Right? Differential form of Gauss law. Right? So why I'm calling it as a differential form of Gauss law? Because if you extend delta dot d bar, right? If we extend delta dot d bar, we have three coordinate systems: Cartesian coordinate system. Cartesian coordinate system is also called as rectangular coordinate system, right? And Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. So therefore, we can express delta dot d bar in all those three coordinate systems, right? So expressing it, we have dou dx bar by dou x plus dou dy bar by dou y plus dou dz bar by dou z, right? So this is the expansion of delta dot. Delta dot in this is divergence of flux density, divergence of a vector. D bar means what? Vector. So divergence of vector, you have studied in vector analysis in mathematics. So divergence of a vector is equal to this. This is the expansion in Cartesian coordinate system or rectangular coordinate system. Similarly, delta dot d bar is equal to 1 by rho dou d rho by dou rho plus here rho d rho by dou rho plus 1 by rho dou d pi by dou pi plus dou dz by dou z. This is cylindrical coordinate system. And similarly, in spherical coordinate system, this can be expressed like this: 1 by r square dou r square dr bar by dou r plus 1 by r sin theta dou sin theta d theta by dou theta plus 1 by r sin theta dou d pi by dou pi. And so this is in spherical coordinate, right? So these are the three different forms in Cartesian coordinate, cylindrical coordinate, and the spherical coordinate. So you have to remember these expressions, right? So if a problem is given, they may be given in cylindrical coordinates or spherical coordinates, whatever it may be, right? So you have to remember these three equations, right? And how to remember, right? So if you look at these equations, they look somewhat complex, right? Looking like difficult to remember, right? So therefore, there is a simple technique to remember these equations, right? Instead of remembering all the above three equations, you just remember this equation, this one, which I am writing now. Delta dot d bar is equal to 1 by h1, h2, h3 dou by dou u, h2, h3 dou u plus dou by dou v H1 H3 dV plus dou by dou W H1 H2 dW. Just remember this. And so instead of remembering the above three equations, you just remember this. Right? It's very easy, no? 1 by H1 H2 H3, and it is expressed in UVW, right? UVW H1 H2 H3. So 1 by H1 H2 H3 into dou by dou U of H2 H3 du bar. So here no H1. In the first term there is no H1. In the second term there is no H2. In third term there is no H3. Right? You just remember this one. Right? And now what is H1, H2, H3, U, V, W for different coordinate systems that we will see, right? So Cartesian coordinate system, cylindrical coordinate system, spherical coordinate system, and here H1, H2, let us say U, V, W, H1, H2, H3. Right? So for Cartesian coordinate system, UVW means X, Y, Z. Right? For Cartesian coordinate system, UVW means X, Y, Z. For cylindrical coordinate system, rho, phi, Z. And for spherical coordinate system, R, theta, phi. Right? And H1, H2, H3, for Cartesian coordinate system, they are 1, 1, and 1. And for cylindrical coordinate system, 1, rho, 1. And for spherical coordinate system, 1, R, R sin theta. That's it. You just remember this table, and that is enough. Right? So you can write all the other about three forms you can write. Right? So you just remember this table. Right? So if you can remember this table, you can express right all the above. For example, let us try to express this in a cylindrical coordinate system. Right? Let us try to express this in cylindrical coordinate system. Right? 1 by delta dot d bar is equal to 1 by H1, H2, H3. Right? So H1, H2, H3. What are those? 1 row 1. Right? 1 row 1. Therefore, 1 by row into row H2, H3. H2, H3. What is H2? Row. H3 is 1. So row du. What is u? U is row by dou row. Right? Plus dou H1, H3. So H1, H3 are 1 and dV. V is pi divided by dou V. V is pi. Right? And plus dou H1, H2. So what is H1, H2 here? H1 is 1, H2 is row dW. W is Z, dz bar, right? By dou Z, right? So this one. So using the above, right? Using the short method, right? So I can write like this. So this is nothing but the whatever the equation I have written above, same equation here, right? So there is no difference here. If you simplify this, this is equal to 1 by rho dou plus 1 by rho dou d pi bar by dou pi bar plus dou dz bar by dou z. That's it. Because here rho, right? Here rho is a constant, right? So here rho is constant here, right? Rho is constant, and that can be taken outside, right? That can be taken outside, and 1 by rho into rho. So rho and rho will get cancelled in the third term, right? So because here the differentiation is with respect to z, partial differentiation. This is with respect to z. So therefore, rho is constant. Rho can be taken outside, and 1 by rho. If you multiply with 1 by rho into rho, rho will get cancelled. We have dou dz by dou z, right? So this is how we can express delta dot d bar in cylindrical coordinate system, right? So therefore, you just remember this one, and so this is the general equation, right? So shortcut method. You just remember this and this table, right? So this table is common for everyone. Even in coming classes, we are going to express so many other terms like this, right? For all, the table is same, right? So and even remembering the table is also very easy, right? Very easy, right? So this is how we can write this, right? And now let us go further. Let us do a problem now. Problem one. Let me take the problem. Find the total electric flux leaving a leaving a surface spherical surface r is equal to 2.5 meters, right? That means radius of the sphere is 2.5. Given the charge configuration a 2 is equal to 2 power minus x square nanocoulomb. On the x-axis at x equal to 0, plus or minus 1, plus or minus 2, plus or minus 3 will be a line charge a line charge rho L is equal to 1 by Z square plus 9 coulomb per meter on the Z axis, right? So this is the problem, right? So standard problem, right? And among this, B bit is very important. The B bit given number of times, right? So try to understand the problem. If you understand the question, you will you can do very easily, right? So understanding question is nothing but getting half the answer, right? So here, find the total electric flux leaving a spherical surface, right? Total electric flux leaving a spherical surface. Total electric flux leaving a spherical surface is I, right? Total flux leaving a spherical surface is Xi. And as per the discussion so far we had, in other words, from Gauss law directly, right? The total flux leaving a spherical surface is equal to what? Is equal to Q, right? Total flux leaving a spherical surface, total flux leaving a spherical surface is equal to total charge enclosed by that surface, right? Total charge enclosed by that surface. So this is nothing but Gauss law, right? That means psi is equal to Q, right? Therefore, A bit, right? Here we have this y-axis and z-axis, right? So a circle, I mean a sphere, a spherical surface, right? So this is a spherical surface of radius 2.5 meters, right? Of radius 2.5 meters. So 2.5 meters radius, right? So radius 2.5 meters in the sense diameter is 5, right? Therefore, here this point is 2.5 and this point is also 2.5, right? Similarly on z-axis also, this point is 2.5, this point is 2 point, right? So because the radius is 2.5, right? And this is the origin, this is the center, right? Center, right? So now coming to a bit, Q is equal to 2 to the power of minus x square nano coulomb, right? So as per the definition of Gauss law, total flux leaving, right? Total flux leaving a spherical surface is equal to total charge enclosed by that surface. So now we need to determine total charge enclosed by that surface. Then we'll get the answer. Total charge enclosed by that surface. What is the total charge enclosed by that surface? Right? The total charge enclosed by that surface On x-axis, charge, right? So charge is located at what? Charge is located at x equal to 0, x equal to plus or minus 1, x equal to plus or minus 2, and x equal to plus or minus 3, right? So like this. So let me indicate so that it will be clear to you. Let me explain the figures first, then it will be clear, right? So right. So x equal to 0. So this is x equal to 0, origin, right? X equal to 0 is the origin, and x equal to plus or minus 1. This is 1. Let us say this is minus 1, and x equal to plus or minus 2, and this is 2, and let us say this is minus 2, and x equal to plus or minus 3, plus or minus 3 in the sense what? Outside, right? So this is 2.5. So here, right here. So this is 3, and this is minus 3, right? So at these points, the charges were located, right? At these points, the charges were located, right? So here, if you observe, there are 5 charges located inside, and there are 5 charges located inside, and 2 charges located outside, right? So one charge is at 0, and another charge is at 1, and 2, right, on x-axis, right? So let us say this is x-axis for our convenience. This is x-axis, right? So here, 5 charges were located inside the sphere, right? At what? At x equal to 0, 1, 2, and minus 1, minus 2. 5 charges were located inside, and 2 charges were located outside, right? But as per the definition of Gauss law, the total flux leaving the surface is equal to the total charge enclosed by that surface. So therefore, charge at minus 3, right? Charge at minus 3 can be neglected. Charge at x equal to 3 can be neglected. No need to consider this, right? Charge at 3 and charge at minus 3 can be neglected. So we have to calculate charge at x equal to 0, at x equal to 1, at x equal to 2, minus 1, minus 2. We have to calculate charge inside, right? So therefore, let us try to determine charge inside. Right? So let us try to determine charge, right? So at x equal to 0, right? At x equal to 0, what is charge? Q is equal to 2 power 0, right? X is 0, right? Therefore 0, right? And this is 1 nano, right? 1 nanovolt. Similarly, at x equal to 1, right? X equal to 1, and what is Q? Q is equal to 2 power minus 1, right? Minus 1, minus 2 power minus 1 square, that is 1. Therefore, this is equal to 0.5 nano. And similarly, at x equal to minus 1, Just a minute. In just a minute, I will once again share my screen. Yes. So right. So at x equal to -1, at x equal to -1, q is equal to 2 power -1, and again same you'll get, right? -1 square is 1, right? And similarly at x equal to 2, 2 is equal to 2 power -4, right? So 2 power -4, we get 1 by 16, 1 by 16 nanocoulomb. And similarly, at x equal to -2, you will get 2 power -4, and this is equal to 1 by 16 nanocoulomb, right? So therefore, the total charge, right? Total charge inside the spherical surface. Here we are not calculating x equal to 3 and x equal to -3, right? We are not calculating the charge here, right? Because these are outside the sphere, right? Outside the sphere. So therefore, no need to consider. The total charge is equal to 1 plus 1 by 2 plus 1 by 2 plus 1 by 16 plus 1 by 16, which is equal to the total flux leaving the surface, right? So total charge Q is equal to, right? Total charge Q is equal to total flux leaving the surface. So this is how we can do the problem. And coming to B bit, right? Coming to B bit. So within 2 minutes I will close. And so B bit, right? So B bit, what is B bit? Line charge is given, right? Line charge, rho L is equal to 1 by z square plus 1 nanocoulomb per meter, right? Line charge is given, right? Line charge is given, right? So therefore, we need to determine total flux leaving, right? Total flux leaving the surface, right? So from Gauss law, we know that total flux leaving the surface is equal to total charge enclosed by, right? Total charge enclosed by. So therefore, Q is equal to, if we know rho L, line charge density, can we determine charge Q? Is there any relationship between rho L and Q? Is there any relationship? Yes, we have. So Q is equal to line integral rho L dV, right? Line integral rho L dV. And this is equal to integral minus 2.5 to 2.5. Rho L 1 by z square plus 1 dz, right? On z-axis, in the problem it was given on z-axis. So on z-axis, what are the limits we have? So this is z, and this is the spherical surface, right? So this one is minus 2.5, and this one is 2.5 on z-axis. So therefore, the limits, what are the limits on z-axis? Minus 2.5 to 2.5. So therefore, limits will become minus 2.5 to 2.5, 1 by z square plus 1 and dz, right? Dz, that's it, right? So therefore, if you integrate this, what will get? 1 by 1 plus z square. Integration is tan inverse z, right? Tan inverse z. Therefore, limits minus 2.5 to 2. Right? So substitute the limits and simplify, we'll get the answer. That's it. So this is how we can calculate total flux leaving any surface. It may be line, right? It may be a sphere, right? It may be anything, right? It may be a plane, right? So any surface we can calculate the total flux leaving, right? So and applications. Let me give the introduction and then we will close, right? So applications of applications of Gauss law, right? So earlier we have determined, uh, I have defined Coulomb's law, right? Coulomb's law, and from Coulomb's law, I have defined electric field, right? From Coulomb's law, I have determined electric field due to point charge and electric field of a line charge and electric field of a surface charge, right? From Coulomb's law, right? So from Coulomb's law, I have defined electric field of a point charge, electric field of a line charge, electric field of a surface charge, right? So electric field of a point charge, E bar is equal to Q by 4 pi epsilon naught R square AR bar, and line charge E bar is equal to rho L by 2 pi epsilon naught rho aero bar. Surface charge E bar is equal to rho S by 2 epsilon naught AN bar. Right? So these are the three equations I have derived earlier. Right? The same equations I can derive right? The same equations I can derive using Gauss law, right? The same equations I can derive using Gauss law, right? So derive, earlier I have derived these equations, you know the procedure, right? And somewhat that procedure is lengthy, right? But whereas using Gauss law, the procedure will become very simple, right? The procedure will become very simple, right? Using a simple procedure, we can derive these three equations. So therefore, in applications of Gauss law, once again, we will derive these equations in a simple manner, right? But to apply Gauss law, to apply Gauss law, the following conditions should be met. The following conditions should be met, right? So if we want to use Gauss law, then the following conditions should be met, right? So without satisfying these two conditions, we cannot apply Gauss law, right? So one is the charge should be uniformly distributed on the surface, right? The charge should be uniformly distributed on the surface. Uniform charge distribution, right? It may be spherical surface, it may be cylindrical surface, right? Or it may be a line charge, whatever it may be, charge should be uniformly distributed, right? And second one, the direction, the direction of the, mm, the electric field, direction of the electric field or flux lines, right? Or flux lines should be perpendicular, perpendicular to the surface, right? Perpendicular to the surface, right? Perpendicular to the surface. So these are the two conditions to be met, right? So then only we can apply Gauss law, right? So charge should be uniformly distributed on the surface. That means what? Charge should be constant, right? Charge should be constant. It should not vary, right? It should not vary with respect to distance, right? So therefore, it should be constant everywhere, right? And the second point is the direction of electric field or flux line should be perpendicular to the surface, as we have discussed earlier, right? So for example, if you take a surface, the electric field should be normal, right? Normal to the surface everywhere, right? It is normal, normal to the surface. Then we can apply Gauss. Similarly, if you consider a line charge, so this is the line charge. So the electric field should be perpendicular, perpendicular to the line, right? Everywhere, everywhere it is perpendicular in all directions, 360 degrees in all directions. Here, 360 degrees in all directions. It should be normal, right? Like, right? Even if you consider a cylindrical surface, even if you consider a cylindrical surface, the electric field should be normal, normal to the surface, right? Normal to the, right? So these are the two conditions. And in the next class, let us see how to apply Gauss law in deriving electric field or in determining electric field with respect to line charge, point charge, and surface charge. All those we will see in the next. And so thank you very much for your patient listening, and we will continue in the next class. If you have any doubts, you can put it on the chat box.